Artificial intelligence in healthcare requires strong explainability and responsible AI practices, particularly in unsupervised learning where models identify patterns without predefined labels, making results difficult to validate. Xinsight is an interactive platform for explainable unsupervised analysis of tabular data, initially motivated by systemic sclerosis, but applicable to any domain where transparency and interpretation are essential. So the workflow starts with exploratory analysis and preprocessing. CSV and Excel inputs are supported. The data overview module provides overall characteristics and statistics across the dataset, with a wide data HTML profile report that can be generated by the user to have a variable level view of the characteristics. The app handles missing value with KNN imputation, with the possibility for the user to have recommendation to find the optimal K. When the data is processed, the user has detail on outliers removal and the processing of the data. Categorical variables are encoded using binary or one-hot encoding, and the app applies adaptive scaling depending on features distributions, which are tested with a Shapiro-Wilk test. A key contribution of Xinsight is comparative clustering. Instead of relying on a single method, the platform let the user benchmark multiple algorithms from classical to deep clustering approach. As previously implemented, the user can have suggestions for picking up the optimal K. The comparative results are shown in a tabular view, and the recommendations include a visual comparison across all the clustering methodologies. The system computes internal validation metrics, which support comparative benchmarking across algorithms and guide the selection of the most appropriate clustering configuration. Xinsight provides generation of dimensionality reduction projection, such as PCA, TSNE, and UMAP. The user can visualize the scatter plots, additional visualization for the clustering evaluation, and have the ability to have a LLM support for interpretation. All prompts used throughout the different modules are implemented directly in the application, and requests are sent via a Google API to the Gemini model. We will see an example in the next module. Global explainability aims to identify the features that characterize each cluster. Xinsight implements three complementary feature importance approaches: surrogate decision tree, importance permutations, and shapely additive explanation. So we can compute feature importance and have comparison across methods, see their details and scores. We can generate cluster profiles to see what feature characterize the most each cluster, feature comparison across clusters. We can extract decision rule from the surrogate tree, again with a tabular view, and a decision tree visualization. The user can also have an LLM support for interpretation. Here's an example of the type of response the LLM can generate. Local explainability focuses on individual instances. The systems provide several complementary explanation methods. We can select several of them, select the patient index, and explain patient assignment to each cluster with a summary and detailed explanation for each methodology. And again, the user can also have LLM support for interpretation. Counterfactual explanation module helps identify the variables that could change an assignment for a given patient. Counterfactual explanations are generated under explicit clinical constraints to protect attributes, such as ranges for biological biomarkers, for example. Like if we took the CRP, the range going from 1 to 10, for example, or enforce immutability for the variable sex, for example. The user can generate counterfactuals using optimization to best fit the domain constraints selected below, or with a die style method that can generate several counterfactual scenarios. So we can generate them, and several visualizations are implemented to see the key differences between generated scenarios and the original cluster assignment. And again, the user has the possibility to have LLM support for interpretation.